Well, we'll now look at the solutions to the problems on reflection and refraction. There are 10 questions in all. Here is the first one. In this first one, there is a man who stands in front of a mirror as shown in this diagram, and his eyes are 1.65 meter above the floor, and the top of his head is 0.13 meter higher. Find the height above the floor of the top and bottom of the smallest mirror in which he can see both the top of his head and his feet. How is this distance related to the man's height? So basically here we're looking at the minimum size of a plane mirror that is required and the height of the mirror from the floor. So when we look at this diagram, we see that in order to see the whole image, the ray of light from the top of the head should get into his eyes, and also the ray of light from the feet should get into his eyes. And we know that the angle of incidence is equal to the angle of reflection. So if we draw a perpendicular, those two angles must be equal. Now let this distance be x, and let this distance, which is the distance of the mirror from the floor, be y, and L is the length of the mirror. So we see that x must be 0.13 by 2 because this is 0.13, so x is half of 0.13. So 0.13 by 2, and again y is half of 1.65 by 2, which is 0.825 meters. Now the length of the mirror is 1.78 minus, now 1.78 is the total length, it's total height. It's 1.65 plus 0.13. So 1.78 minus 0.065 plus 0.825, because you can see that the length of the mirror is actually the total height of the person minus x plus y. So when you do that, you get the answer as 0.89 meter, which is the minimum length of the mirror, and the bottom of the mirror is 0.825 meter from the floor, because that's y. Okay, y is 0.825 meter from the mirror. How is this distance related to the man's height? The length of the mirror is not related to the man's height because it does not depend on where he stands from the mirror. In question 2, a scuba diver training in a pool looks at his instructor as shown in the figure. What angle does the ray from the instructor's face make with the perpendicular to the water at the point where the ray enters? The angle between the ray in the water and the perpendicular to the water is 25 degrees. All right, just neglect all this stuff there, right? So here is the diver and this is the instructor. And so you can see that the ray is from the diver reaching the eyes of the instructor. But it appears to the instructor as though the diver is here, because the eye always thinks that the ray is coming from straight behind, so it appears to be coming from straight behind. And we are asked to find the angle made falling on the instructor's face with the perpendicular. Okay, so let's get into this. Let me complete the diagram and explain this now. So these are the angles. Theta 1 is the angle of incidence which we are trying to find, and at 25 degrees is the angle in the water. So by Snell's law of refraction, n1 sine theta 1 is equal to n2 sine theta 2. N1 is the refractive index of this material, which is air. Theta 1 is this angle. N2 is the refractive index of water. And theta 2 is the angle in the water, which is 25. So the refractive index of air is 1. So 1 times sine theta 1 is, the refractive index of water is 1.333, so sine 25. So when you rearrange this, you make sine theta 1 is 1.333 times sine 25 divided by 1. And that gives us the value of sine theta 1 as 0.5634. And from this, we can find the inverse of that. Find the inverse of 0.56, sine inverse of 0.5634, and you get the angle as 34.2 degrees. So this is a continuation of the previous problem, and in this question we have to find the height of the instructor's head above the water. Okay, so and find the apparent depth of the diver's head below the water as seen by the instructor. Okay, so both of that. So this question has been already explained, so I think it should make more sense now. And here N1 sine theta 1 is N2 sine theta 2. We did all this and we did find the angle made. I'm just repeating that. You know, we got the angle here, sine theta 1, and then we get the sine inverse, which gives us the angle as, I can't remember what the number was. We're going to see it. All right, that's 34.2 degrees is what we got. So that was theta 1, theta 2 is 25. And now from the geometry of this diagram, tan theta 1. So to see tan theta 1, you have to imagine a right angle triangle here. That right angle triangle, okay? That right angle triangle. In that right angle triangle, you see that the opposite side of this angle is going to be this. This is given as 2 meters. And this is going to be the adjacent side, which is what we're trying to find. Okay? So let's call that h. So clearly tan theta 1 is 2 divided by h. So from there, since we have the angle theta 1, we can substitute the value of theta 1 and find the height. Rearrange the equation. H is 2 by tan theta 1, and then 2 by tan 34.2 gives 2.94 meter. Okay, now I have completed the triangle. Now for the third part, in the third part, or B here, we have to find the apparent depth of the diver's head below the water. So we're trying to find this now. The actual depth is 2 meters, but the apparent depth is less than 2 meters, as you can see, and we got to find that. Now I don't think I found that. Well, I'll have to use the triangle here, similarly, and find it. Okay, total internal reflection to make an efficient corner reflector. And if there is air outside and the incident angle is 45 degrees, what must be the minimum index of refraction of the material from which the reflector is made? So the picture actually shows the astronauts trying to set up a corner reflector on the moon. Now, a corner reflector uses total internal reflection. And when it says what must be the minimum index of refraction, that means we're looking for the critical angle. That's when the minimum value of index comes out. Okay, so minimum refractive index corresponds to critical angle. And so once again we use Snell's law. When we use Snell's law, we can find the critical angle. But remember that whenever the angle of refraction is the critical angle of incidence rather is the critical angle, the angle of refraction is 90 degrees. So that's why in this equation you see sine 90 here. So when the angle of incidence is the critical angle, the angle of refraction is 90 degrees. So when you apply Snell's law, you get that when you rearrange and get N1. But sine 90 is 1. And N2 in this case is 1. Okay? Because it's going from the mirror into air. Mirror into air. So the second material is air. The refractive index of air is 1. But I've used the exact value here, which is slightly more than 1. So it's 1.000293. Okay, divided by sine 45, the critical angle is given as 45. So N1 is 1.414. So that's the refractive index of the material. This question, a narrow beam of light containing yellow 580 nanometer and green 550 nanometer wavelengths goes from polystyrene to air, striking the surface at a 30-degree incident angle. What is the angle between the colors when they emerge? How far would they have to travel to be separated by 1 millimeter? So there are two colors and their wavelengths are different. When the wavelengths are different, the refractive indices are also different. So yellow and green have a slightly different refractive index. The angles of incidence are the same, it's 30 degrees. So all we have to do is apply Snell's law of refraction and find out the angle of refraction for each case, for each wavelength. So that's just a picture showing refraction where it's bending. So here is Snell's law. And we're trying to find theta 2, so rearrange that and find theta 2. Theta 2 is sine inverse N1 sine theta 1 by N2. Remember, it's coming out into air, so N2 is 1. I've taken the approximate value here, 1. And so since we have the general equation, now we can apply it first to yellow and then to green. So here is the refractive index of the material for yellow, which gives us this angle. And do the same for green. You'll see that the refractive index, which is slightly different, remember it's 1.493 instead of 1.492. And these values are actually given in the problem. They'll be given. It's just that I forgot to print it out. So you get the angle of refraction for the second color, for green. And to find the angle between the colors, just find the difference. And you get that small angle or angular difference between the colors, 0.0430 degrees. So you have, which is that yellow, and then you have green at a slightly bigger angle. So that is what you mean by dispersion, where the colors come to focus on a screen at different points. See? And then the second part, how far would they have to travel to be separated by 1 millimeter? Now to find that, you just use trig. So here are the colors, and you have the angle between them, and we're trying to find this distance. And from this approximate triangle, because it's such a small angle, tan theta is opposite side by adjacent side. So tan theta is y by x. And then make x the subject, and that gives y by tan delta theta. Delta theta is 0.0430. So put that number in, find it, you get the answer. Now it has to be 1.33 millimeters. So that's 1.33 millimeters. So they're separated by a small distance. Number 6, a very simple question. You note that your prescription for new eyeglasses is negative 4.50 diopter. So the D there stands for diopter. What will their focal length be? Now, first of all, when you see a negative on the power, you know it's a concave lens, because a concave lens has a negative focal length, yes, and negative power. Okay, so I should have done a better job. I drew the diagram of a convex lens, and that's convex, and that is a positive focus, okay? So, but the question refers to a negative focal length, and all you got to do is remember that power is 1 divided by the focal length. But the focal length has to be in meters. So when you rearrange that, you are going to get F in meters. F is 1 by P, which is 1 by negative 4.50 diopter, which gives negative 0.222 meter, which is negative 22.2 centimeters. Okay, so the negative focal length comes from the negative power and shows that it is a concave lens. Okay, because then concave lens is again used to correct short sight. All right, to correct short sight, where the person can see stuff that's really close very clearly, but when it is further away, the person is not able to see clearly. So that's short sight. And it's corrected using what? It's corrected using concave lenses. That now is question number 7. A doctor examines a mole with a 15.0 centimeter focal length magnifying glass held 13.5 centimeter from the mole. Where is the image? Okay, I'm not going to read the remaining part of the problem. Let's first focus on this. So the focal length is 15 centimeter and it's a magnifying glass. What does that say? A magnifying glass is a convex lens. A convex lens. That means its focal length is positive. So F is positive, and it's held 13.5 centimeter from the mole. So that 13.5 centimeter is the distance of the object. Yes. So the distance of the object and the focal length are given. All right. And this is the kind of diagram that we have, because the object is inside the focal point, because the object distance is only 13.5 while the focal length is 15 centimeters. So whenever the object is inside the focal point, the convex lens produces a virtual image that is magnified, as you can see. And to find it, we use the law of distances, which is 1 by DO plus 1 by DI is 1 by F. Here we're looking for DI. So make 1 by DI the subject, because we're given the values of F and DO, and we're looking for DI. So 1 by DI is 1 by the focal length in meters is 0.15, and DO is 0.135. So when we do this math, you get this. But remember, that's 1 over DI. So when you flip it, you get DI, which means you have to flip the right side. So it will be 1 divided by this number. Remember the negative. And you get negative 1.35 meter. So DI is negative. What does a negative show? It shows that it's virtual. It shows that the image is on the same side as the object. It's a virtual image. It's an upright virtual image which is magnified. Now let's go to the B part. What is its magnification? There are two formulas for magnification. One is, magnification is negative di by do. Do not forget the negative there. So since we have di and do, that's the formula that we could use. At least this time. And you get the magnification as plus 10. So the image is 10 times the size of the object. So that enables us to do the C part. It says, how big is the image of a 5.00 millimeter diameter mole? So use the other formula for magnification, which is HI by HO. And since we have the magnification now as 10, we can find the height of the image simply by multiplying the magnification with the height of the object. I'm just keeping it in millimeters. So the image is 50.0 millimeters. A camera with a 50 millimeter focal length is being used to photograph a person standing 3 meters away. How far from the lens must the film be? Okay, so here the focal length of the lens is given, 50 millimeter, and the person is the object, and so the object is 3 meters away, and we have to find how far from the lens the film is. That's the image distance. As you can see, person is here, that's 3 meters. We're looking for how far away the image is from the lens. So once again, we use the law of distances, which is 1 by do plus 1 by di is 1 by f. And we're looking for di again. So that's the law of distances. Make 1 by di the subject. And you would get 1 by di is 1 by f minus 1 by do, right? And you have to use consistent units for focal length and do. So I've converted both into meter. A focal length is 50 millimeter, which is 50 divided by 1000, and then 3 meter is already in meters. So when you do that, you get this. Remember again, it's 1 by do. 1 by di. So di would be the reciprocal of that. That gives 0.0508 meter. So that's how far the film must be. In the B part, if the film is 36 meters high, what fraction of a 1.75 meter tall person will fit on it? So here we're given the maximum size of the image that's possible, which is the size of the film. That's 36 millimeters, and so the entire object will not fit on it, obviously, so we're going to find out what fraction. That means we just got to find the magnification. And there are two formulas for magnification. Here, magnification is HI by HO, which is equal to negative DI by DO, okay? So those are the two formulas for magnification. And from these two, we can make HI the subject, and you get negative DI by DO times HO. So HI is 0.0508 by 3 times 1.75, which is the height of the object, which gives negative 0.0296 meter. And the C part at 3 meters, is it reasonable? Yes, because the height of the image is only 29.6 millimeter, and the height of the film is 36 millimeter. It's entirely possible to fit the whole image on the film. In this question, an object 1.50 centimeter high is held 3 centimeters from a person's cornea, and its reflected image is measured to be 0.167 centimeters high. What is the magnification? So here we have the height of the object is 1.50 centimeter. It's 3 centimeters from the person's cornea, which is the object distance, and the image is 0.167 centimeter high. So the height of the object and the height of the image are given. Therefore, we can find the magnification. Magnification is HI by HO, HI by HO, or negative DI by DO. So in this case, we can use magnification is 0.167, which is HI, divided by HO is 1.50. Both are in centimeters, so that's okay. And we get the magnification is 0.113, actually 1113. And B, where is the image? So now we have to find DI, the distance of the image. So you can see that the distance of the image must be somewhere inside, okay? Maybe on the retina, if it is to be clear. So now we can use the other formula for magnification, which is negative DI by DO, and find DI. Magnification, we already got it as 0.1113 times DO, which is the object distance is 3 centimeters. That gives us negative 0.334 centimeters. So now in the C part, find the radius of curvature of the convex mirror formed by the cornea. So you see that the cornea here acts like a convex mirror now. And to find the radius of curvature, you take twice the focal length. So first we have to find the focal length and find twice that value. So let's try to find the focal length using the law of distances, which is 1 by DO plus 1 by DI is equal to 1 by F, but I've rearranged it to get F. So you can see it's whole raised to negative 1, which means we get the value of the focal length directly. So when we make the calculations, now that's DI, this is DO, you get the focal length to be negative 0.376 centimeter. So the radius will be double that, which is negative 0.752 centimeters. So that's the radius of curvature. And the question says that this is the method or the technique that optometrists use to measure the curvature of the cornea, which they need to fit on a contact lens, because you know the curvature of the cornea for each person is different, and the contact lens needs to have the same curvature so that it can fit snug on the cornea. A camera with a 100 millimeter focal length lens is used to photograph the sun and moon. What is the height of the image of the sun on the film, given the sun is 1.4 times 10 to the power 6 kilometers in diameter? So that's the size of the sun, which will be taken as the height of the object, and is 1.50 times 10 to the power 8 kilometers away. So, and that is DO. And we are asked to find the height of the image of the sun on the film. So that means we are asked to find HI. Okay, so we given the focal length, which is 100 millimeter. We have DO, and we also have the height of the object. So in order to find that, so that is the camera. You see that the object is there and the image is to be formed on the film. Using the law of distances again, we can calculate DI. Now once again, I'm straightforward going into 1 by F minus 1 by DO raised to negative 1. And we have to really do this problem carefully, because the distances involved are so big on one side and small on the other. You see, this is a small value, this is a big value. So you got to be very careful when you do this problem. So let me show you what I have done here. di is 1 by f minus 1 by do. How? Because raised to negative 1 means 1 by the whole thing. All right, so that's what you get for di. And magnification is negative di by do. So this whole thing is di. And then you got to divide by do. So that's what I've done. So I'll put a negative because of this negative. And then you have this whole thing as di. And then the do, which is this one. So I'm going to rearrange that. You see, I take the lowest common multiple here. I put do minus f by f do. And then there is a do outside, you can see. So the do's get cancelled, leaving me with negative 1 by, now I can divide this by this, which will give do by f, and then minus f by f is 1, so that's do by f minus 1. And here I'm substituting the values. So magnification is minus 1 by do by f. Now do is this big number. Focal length is 0.1 meter minus 1. On doing the calculations, I get this extremely small number with a negative. And then I know magnification is hi by ho. And so since we have the magnification as negative, that small number is equal to hi by ho. We're asked to find hi. So that will be that number multiplied by ho, which is the diameter of the sun in meters. That's why it's 1.40 times 10 to the 9. I changed the kilometers into meter. And when we do the math, you get negative 9.33 times 10 to the negative 4 meter, which in millimeters is negative 0.933 millimeter. Now the reason we had to go through this process is because of the numbers being really big and small. So if you do it any other way, you're going to get an approximate, very approximate and wrong answer. So it's only in this kind of a problem where you're trying to get the image of an object that is really far, far away that you have to do all this math. I just wanted you to see that becomes necessary in these particular cases. So I hope all these problems are understandable here. Mainly we have used the law of distances, then the two formulas for magnification, and then we have used Snell's law when it comes to refraction. So good luck and see you on the next video.